Okay, today we're going to learn about integration by parts. And so how you find integration parts, use this whenever you have an integrand that has a product of polynomials and transcendental functions. So anytime you have a product of polynomials and transcendental function, remember transcendental functions are trig functions, exponential, logarithms, things like that. So our rule for integration by parts is if I have u, the integral of u times dv, we use in terms of x and dv is in terms of x. If I have integration of parts of the integral of u dv, that's going to be equal to uv minus the integral of v du. The hardest thing about integration by parts is figuring out which function is going to be your u function and which function is going to be your dv function. So the easiest way to do this is look at your two functions and let u be the function that is the easiest to integrate, and then easiest to differentiate, and when the derivative is more simple than the original problem. Let dv be the function that you can integrate without too much problems. Now, to help you kind of figure out which way to go, there's a lot of very common functions that are multiplied together, and we're going to look at what our u would be for each of these functions. So if I have a polynomial times a sine function, or a polynomial times a cosine function, or even a polynomial times an exponential function, my u will always be the polynomial. And my dv will be the other function, so everything that's left over. So dv in the first one would be sine of ax dx, and in the last one it would be e to the ax times dx. For example, let's say we have e to the ax times sine of ax dx, or e to the ax times cosine of ax dx. In these two cases, in this case, you're going to let your u be the trig function. So u will be sine of bx or sine of the cosine of bx, and your dv will be e to the ax dx. So let's say I have the integral of x to the n times the natural log of x, or the integral of x to the n times the arc sine of ax dx, or I have x to the n times the arc tangent of ax dx. So in these cases, it's not the polynomial. This is one of the few cases where you wouldn't pick the polynomial to be your u. Instead, it works out easier if you make your u the natural log of x, or the arc sine of x of ax, or the arc tangent of ax. Now the reason for that is, remember, the derivatives of those are all rational functions, and that would be easy to work with and maybe simplify down with that polynomial function that we integrate. Reminder, you must know the formula for integration by parts. So the formula for integration by parts is if you're given the integral of u dv, that's going to be equal to uv minus the integral of v du. So let's try our first example. So in this problem, let's find the integral of x, natural log of x dx. What is your u in this case? I hope you picture u to be the natural log of x, not the polynomial. So the derivative of the natural log of x is 1 over x. And so that means that if the natural log of x was my u, my dv is what's left over in my integral, which is x dx. Now to find v, you integrate dv. So I'm going to find the integral of x, which is 1/2 x squared. And now I'm going to plug this into our formula. So remember, our formula is uv minus the integral of v du. So substituting in our u, we'll do natural log of x times 1/2 x squared minus the integral of our v, which is 1/2 x squared again, times our du, which is 1 over x dx. All right, let's simplify now. Multiplying the natural log of x times the 1/2 x squared, we get x squared over 2 times the natural log of x. And then simplifying this integral, I can factor out my 1/2 and simplify my x's. And so now see how that's simplified down? That integral is now just the integral of x, which we can easily figure out because we know the integral of x is just simply 1/2 x squared. And then simplify down, we get x squared over 2 times the natural log of x minus 1/4 x squared plus c. Now you can leave it like this, or if you want to, a lot of people like factoring out or GCF. Sometimes it's just easier to evaluate if you have a definite integral to evaluate in. And we could write it like this. So either one of these last two lines would be acceptable answers. Okay, now you know it doesn't stop there. Sometimes you have to use integration by parts multiple times, and we define a new u. So again, remember our integral by part is u dv is equal to uv minus integral of v du. So in this case, we have a polynomial and exponential. Which one would you choose your u to be? I hope you choose your u to be x squared. So the derivative of that is 2x. So that means my dv is going to be e to the x dx. So the integral of that is just e to the x. So plugging it into our formula, we have x squared times e to the x minus the integral of e to the x times 2x dx. Okay, simplifying that down, making it look a little prettier. I can factor out my 2 from the integral, and I still have x e to the x dx. Oh, that's still a product rule. So this is an example where we got to find another u. So looking at the x times e to the x, you find your second u, which is again the polynomial, so I'll call it x. The derivative of that is 1. And then my dv is going to be e to the x dx, and the integral of e to the x dx is simply e to the x. So don't forget to copy down that first term in that -2. So we got x squared e to the x minus 2, and then in brackets, we're going to put our integral of x e to the x using our integration by parts formula again. Okay, so let's do this again. Now don't forget, now we have a brackets here, so we're going to distribute that -2 to each of those terms. And now we have the integral of e to the x dx. Now that is no longer a product rule, so we can actually find that integral. And we are finished. But most people, again, would factor out their GCF of e to the x, and you might see it written like this. So either one of these bottom numbers would be a correct answer. Bottom lines would be a correct answer. Okay, I want you to try the embedded question. Okay, when you have to do integration by parts multiple times, it can get tedious because you can have 3 or 4 integrations of this. So there's another approach to this called the tabular method. Now we use the tabular method when we have the form where you have a polynomial times a trig, sine of a to the x, or a polynomial times cosine of the x, or a polynomial times e to the x. These 3 cases work great with the tabular rule. Basically, if your u is a polynomial, you can probably use the tabular rule. Okay, so you set 3 columns up. We're going to do our sine, our derivatives, which is our u values, and our integral, which is our dv values. You always start with the polynomial, the u term. So our u in this case is going to be x squared, and our dv is going to be that sine of 4x dx. So start your first row. Is going to be under the derivative column is going to be x squared, and then you're just going to take the derivative of that and you're going to keep differentiating it until you get to 0. So that'll give us 2x, 2, and 0. Then you're going to take your dv, which in this case is sine of 4x, and you're going to integrate that as many times until you get to that row that has the 0. So in this case, we're going to integrate it 3 times. The integral of sine of 4x is -1/4 cosine of 4x. The integral of that is -1/16 sine of 4x. And the integral of that is 1/64 cosine of 4x. The last thing you're going to do is put your sine column in. Now, the sine column, you just alternate signs, always starting with positive. Okay, now how does this table help us? Well, what you do is you go across and diagonal. So that means my first term is going to be positive x squared times the -1/4 cosine of 4x, because that gives me my uv. Okay, then across and diagonal for our next term, so that's going to be a -2x times a -1/16 sine of 4x. And again, across and down. You keep going across and down until you run out of integrals. So this is going to be a +2 times 1/64 cosine of 4x plus c. And now you've integrated that. See how fast that was? I love this method. So now we're just simplify it down, get rid of all parentheses, and we end up with this equation. Again, you could have factored out the 1/4. I'm just not going to bother this time. Okay, next thing we're going to do is application problems. We can apply this to real life situations. So in this case, The estimated rate at which oil will be produced from a certain oil well T years after production has begun is given by R of T is equal to 100 TE to the negative 0.1 T, thousands of barrels per year. Our job is to find an expression that represents the total production of oil at the end of T years. So what you need to do is first identify some variables. So I'm going to let big T of T represent my total production of oil from the well at the end of T years. And I'm going to let T start at 0 and go up. So T is greater than or equal to 0. So if I take the derivative of the total production of oil, that gives me the rate of the oil production, rate of change. That's what derivative is. And so they gave us that the rate of change in thousands of barrels per year was R of T. So how I've set this up, my big T prime of T is equal to R of T. Okay, so, but I don't want big T prime of T, I want T, big T of T. So that means I need to find the integral of RT, or the integral of 100 TE to the negative 0.1 T. So let's factor out the 100. And I end up with TE to the negative 0.1 T. That's a product. I have two terms. I'm going to let my U be the polynomial T. I'm going to let my dV be my exponential function. We'll do this with the tabular method. Okay, so the derivatives of T is T1 and 0. The derivatives of our dV is negative, well, let's simplify that. That'd be negative 10e to the negative 0.1 T. And the integral of that is just 100 e to the negative 0.1 T. And now remember, signs alternate, positive, negative, positive. And to put this together, we go over and across, over and diagonal. So that's T times that negative 10e to the negative 0.1 T minus that 1 times the 100e to the negative 0.1 T plus C. I just realized I made a big error. I hope you figured out what it was. Let's go back to this top up here. Remember at the very beginning when I set up my integral, I forgot I brought out that 100, so we need to bring that 100 over here as well. And so I'm going to distribute this 100 through. Now notice I'm not going to multiply C by 100 and write 100C. It doesn't matter. C is an arbitrary constant, so I'm just going to write C again. Now I need to figure out that C value. So remember it told us they begun production at T equals 0 years. So if they began the production at T equals 0 years, at time 0, there was 0 amount produced. So I'm going to let my T equation, my big T equation here, if I let little t equals 0, I can set this equation equal to 0 and solve for C. And I get C is 10,000. So the problem asks us to find an equation that represents the production, and that would be this T of T, which is negative 1,000 e to the negative 0.1 T times in parentheses T plus 10, close parentheses, plus 10,000. So that's how you do integration by parts.